All right, here we go. Optimization. This is the first real fun application of the derivative. We've already applied it to like curve sketching a little bit to get information about a function, but this is the fun part because this is where math meets words, right? And math alone is fun. Words by themselves, playful. But when you combine them, you get lots and loads of fun, right? Optimization. That is a word, right? And what does it mean? You've encountered that word or the root of the word, not optical or Optimus Prime or opossum. That's what they suggested last period. Where have you heard the word optimize? Or what does it mean to optimize? What?
To enhance, to be the best of its ability.
To be the best of its ability. And is there anything usually that prevents it from being infinitely bestest?
Infinitely worse stuff.
Yes. Are you limited? Are you limited to how great you could be? That was Tally, by the way, who brought me my Dasani. Are you limited in any way at how great you could be? Is there anything holding you back? Lack of knowledge. Could you acquire that lack? Could you fill that void? You could. And what would be holding you back from filling that infinitely? Human nature. We're limited by human nature, right? By human nature, time is finite. At least for us it is, right? Time is finite. Lack of resources. There are limitations that limit our growth, right? That prevent us from being as great as we otherwise could be. Now, making excuses and citing those reasons is one of the things itself that holds you back, right? So you just do the best you can where you are with what you have. Who said that? Teddy. Yeah, Teddy. Okay? And so that's what optimization is going to be about. The key words in optimization are maximize. You're trying to maximize your potential. You, Walden, might be trying to minimize your potential. That's another word. Not potential. What's another? What would you try to minimize? Huh? Backpacking? Bacteria. Pain. Back pain. Yes. You would try to minimize back pain. Anytime you're trying to maximize something or minimize something, whether you're trying to minimize back pain or maximize, what did we say it was? Potential? Potential, yeah. It's going to be optimization. Another key word besides maximize and minimize are anytime you use a superlative case. What's a superlative case? Most, cheapest, strongest, fastest, ugliest, roundest, bestestest, okay? The most this, the least that. So anytime you see the superlative case, you're going to be using optimization. But in every case of optimization, there is going to be some limiting factor, something that is holding you back, that is making you stay short of where you otherwise want to be, whether it's a high or a low goal. Okay, and we call that a constraint. It's a constraint. We are essentially going to be looking, though, for something that we already know how to find. We're going to be looking in this section for absolute extrema, which are also known as what type of extrema? Global or just extrema, right? These are absolute maxes and absolute mins. And when we did them before, we did it on a closed interval. And what theorem applied? The EVT. So this is really going to be the EVT applied. Maybe. Okay, the EVT does say what? What does the E stand for? Extreme value theorem. Good. And what does it say? Anyone? What does it say? If continuous on a closed interval, then? Or is there another if part? Sorry. Oh, is it also differentiable in the open? For the EVT? Ah, that's MVT. M for slopes. No, not good. Slopes. It's the IVT and the EVT that just have the first if, right? If it's continuous on a closed. Then the EVT guarantees that we're going to have both a max and a min. Okay? And so we found it by evaluating the function at the endpoints. Yeah? But there were other candidates that worked. What were they? Critical values. So this section is all about taking derivatives, imagine that, set it equaling to 0 to find critical values, and then plugging them back into the original function and looking to see which one's biggest and which one's smallest. Does that sound hard? No. Does it sound fun? No. Yes. All right, so To kind of give you a taste of what it's going to be, I'll use example 1, and I'll have to modify it a little bit. I always say I imagine that this is what kind of the Greek youth were doing back in the toga days. You know, in Archimedean style, they'd have togas and sticks, and they'd do math problems in the sand. And this was back when maybe MySpace was still popular, you know, before Twitter and Facebook and Instagram kind of took over and started squandering their times, right? Although maybe MySpace, are there any MySpace pages left for the Greek youth of 300 BC? Probably not anymore. Are there any MySpace pages left out there at all? They're there. They're there, yeah. Probably so. All right, here we go. Example 1. It says to find two numbers, and I'm going to add up here, I need to add this. Find two positive numbers. Kind of important. We discovered that last period. Find two positive numbers whose sum is 60. No one's going to volunteer how smart you are? Two numbers whose sum is 60? 29 and 30 what? 29 and 31. 17 and whoo. 17. Oh, is that the Taylor Swift? It's good to be 17. Can't wait till I'm 43. Can't wait till I'm 43, because then those would add up to 60. That'd make a horrible song. You know what? Those are all numbers that add up to 60. And how many more are there? There's quite a few. There's actually infinitely many, right? Because you don't have to restrict yourself to integers, do you? Now, could one of them be 61? And -1, right? But does that work with my little additive qualification? No. Okay, so there's a catch. That would be a really boring competition, right? Maybe for like babies and togas, right? That would be a good one, right? But the catch here is we're trying to find two numbers whose sum is 60 such that, here's the kicker, such that the product of one of those numbers times the square of the other one is a maximum. We want one of them times the other one squared to be as absolutely big as possible. Now you know what we could do? We could call one of these one numbers and the other one the other number. Which one would you call one number and which one would you call the other number? 31 is one number and the other one would be the other one. Yeah. Well, we could do trial and error. If we want to have the product of one times the square of the other be as big as possible, it makes sense to square which of the two, the larger or the smaller? The larger. So I think we can kind of reason that. So 17 times 43 squared is 29 times 31 squared is I don't know. We can start making a list, right? And just have all those products, and then if we make an exhaustive list, and by exhaustive I mean we get tired and we peter out and we stop before we get through all the combinations because we're exhausted. Whew. Does that mean we found it? No, because just because we stop doesn't mean, even though we have found one that's the biggest, doesn't mean it's the biggest. So no amount of trial and error is going to get us to our answer. So how can we definitively do it algorithmically? By a sequence that works every time. Yeah, we can use calculus, right? And BOTC, and that's going to require some equations. So the first thing about optimization is you have to extract your own juice, right? We're handing you oranges, and we're going to make you make orange juice. We learned last period that just because you're handed lemons, you don't have to make lemonade. In fact, actually, that's a very, very easy thing to do when you're handed lemons. The better thing to do would be to make like lemon squares, right? Which are much better than lemonade. And if you're going to make lemonade, at least get on the corner and start selling the stuff. Be industrious. But we're going to be handed oranges, and we're going to make our own, not orange squares, but orange juice. We're going to squeeze it. All right, so here we go. Here's the anatomy. We got 5 minutes. Let me get through the quick anatomy. Try not to get me off task anymore. Here's the anatomy of a optimization problem. We know that it's a word problem. It's an application. Not a real interesting one, but it's an application. We know it's an optimization problem because it says maximize. And anytime you use the superlative case or it says max or min, it's optimization. You want to first write a primary equation, okay? A primary equation. And it doesn't necessarily have to come first, but I call it the primary equation because it's the optimal equation. You can call it that as well. It's the one that you're going to be working with. Well, we are trying to find the product of one number times another number. I don't know what those numbers are, so the step one maybe is to assign variables to those two unknown numbers. That's what we do in algebra. What do you want to call the two numbers? A and B and C, F and G, X and Y, theta and mu? How about the other people chose B and C because it was BC class. If you want to use the Greek letters, go for it. Now, which one of those do you want to call one of them, and which one do you want to call the other? C is one and B is the other? So C times B squared? Okay. It doesn't matter. You can do C times B squared. You could even do B times C squared. You know why? It doesn't matter at this point. But here's what's important. When you find these numbers, and you find B and you find C, now it matters. Because the one that you call B eventually, or ultimately, is the one that's going to have to be squared. And it should be the larger of the two, yeah? Okay. Now, I need to give that a name. That represents a product of two numbers. So what do you want to call that function? The product function P? Yeah, if you want to keep it simple, that's what I would recommend. Call it whatever you want. We're trying to maximize that. So remember, maximum values can occur at either an endpoint or a critical value. Do we even have an endpoint? We're looking at positive numbers. We're on the interval from 0 to technically infinity, right? Now, we can kind of trim that off a little bit and say that the top number has to be less than 60, because if it's bigger than 60, the other one to add up to 60 is going to be negative. So we could say it's from 0 to 60. Can we include the endpoints? Well, is 0 positive? No, so, I mean, if we wanted to be sticky about it, we could then maybe do that. But if 60 is one of the numbers, what's the other number? It would have to be 0. So technically, we really can't even use 60. So we now have thought of an open interval in which B and C can live. Does the EVT apply on an open interval? No. And that's the thing that is sometimes difficult about optimization, is that if you were ever asked to justify that you have an absolute maximum in, you can't use the EVT, which is the closed interval argument. Evaluate the function at the endpoints and the critical values. You're going to have to justify some other way. No, because how many positive numbers are greater than 0 but less than 1? Infinitely many. And one of those might be the solution. Yeah. Okay, so this is what we call a relevant domain. And every single word problem that uses a mathematical model to describe it is going to have a relevant domain. Just because a polynomial has a domain of all real numbers doesn't mean that the application in which you're using it is going to have values of all real numbers, right? Especially if you're talking about like time or something like that. Negative time can make sense in terms of extrapolating backwards, but generally it doesn't. Price of gasoline, right? Negative doesn't make sense. That'd be great if you could get in line for gas and they pay you to take it, right? Yeah, fill me up. That one wasn't the tricky one on the test, was it? That one, hopefully. Okay. So here we go. I want to take the derivative and set it equal to 0, but here's the problem now. I have my primary equation for P product in terms of two variables. And I don't know multivariable calculus yet. So I need to somehow get this as an equation of a single variable. I need it to be a function of C, or I need it to be a function of B, one or the other. I need it to be in terms of one variable. And as you're eating lunch, you need to tell me when you get back how we're going to do that, because I don't know. But I want to know, and I know y'all can tell me. All right, have a great lunch. See you when you get back.